Hello! So in this video, we're going to be talking about the language of context, i.e. the sets. So these are things that I've sort of used already, but sort of in very general terms. So now we're actually going to go through the actual sort of precision, notation, and mechanics of sets. Okay? So just right off the bat, there are sort of two key ways of notating a set. Either way, we sort of signify a set or sort of notate a set using braces. So first way I'm going to mention, although like I said, they're both going to have sort of common aspects, but the first one I'm going to go through is the list method. And this is very much what you sort of would expect, but keep in mind a set can be infinite, like the set of all whole numbers, but it can be finite too, and finite's usually where you use the list method. So if I was going to have a list of numbers, say the numbers 1, 2, 3, and 4, in set notation, I would do that by having an open brace, right, curly brace here, 1, comma 2, comma 3, comma 4, and this would be sort of an example of a set. And in fact, this is just saying the set, listing the set. I could also give it a name. By convention, we give capital letters. We name sets with capital letters. So I could call this thing, say, A. Okay? So A is the set of numbers 1, 2, 3, and 4. And in general, when you see a list, what you sort of want to be able to read this as, the open parenthesis, this thing you want to think of as the set of, then we have the actual pieces, so the set of 1, 2, 3, and 4, and then this closed brace just signifies the end of the set. So with lists, it's pretty straightforward. It gets a little, I'm doing this because these are going to be common for the next method where things are a little more complicated. Now, some basic sort of pieces about sets, some basic information about sets, regardless of how they are sort of notated or made or listed out. First and foremost, it is, by convention, we only include any value once. So I sort of shouldn't write the set 1, 1, 2, 3, 4. Strictly speaking, whether or not this is a technically correct, technically incorrect thing to write is sort of debatable. For the sake of this class, and I'm sure in sort of future math classes, this is not something that you should write. So usually what we do is if we have something like this where we have the set of, right, the set of 1, 1, 2, 3, and 4, this is equivalent to the set just 1, 2, 3, and 4, meaning that we are reducing by getting rid of the duplicates, okay? So we should only write each entry once. It should be a unique entry, okay? Now with lists in particular, again, this is one of those things where I could do, say, 1, 2, 3, 4, dot, 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 right? So use the ellipsis, the dot, dot, dot bit. Now, strictly speaking, this is an acceptable way of listing values. The key here, though, is you need enough sort of elements, enough pieces in the set where each of these entries we call an element of the set. So you need enough elements, 1, 2, 3, and 4, where you've established whatever the pattern is. So here, 1, 2, 3, and 4, I am sort of clearly adding 1 each time. Now this gets into a hazy thing because it turns out that you actually can't sort of well define a pattern. You can always find a way to make the next value, you can always find some pattern to make the next value whatever you want it to be. And so it's very sort of difficult to make this a rigorous process. And for that reason, it's generally a good idea not to do that if you can sort of avoid that. But nonetheless, obviously, I can't sort of list every number without a dot, dot, dot if I'm going to be talking about infinite sets, right? Because by definition, there's infinitely many things. I can't write all of them down, right? So this gets into the next piece of it, which is the set builder notation. So let me sort of write that out. So this is a list method as opposed to set builder notation. So set builder notation is a notation that describes the elements in the set with some property. So for example, if I wrote something, so let me write out a set builder and then I'll go through what it means. So again, I have the set of, open here, I could say X, two little dots, and then I could say X, let me do this. I'll introduce a bunch of stuff here, all of which we sort of need to introduce. So here, set builder notation, the way I can tell is that I have these two little dots. Sometimes you will also see instead of two little dots, sort of equivalently, a long vertical bar. So these two sets that I'm writing here would be considered the same exact thing, right? I can do the colon or I can do sort of a long vertical bar. So if I were to read this, again, I have this open bracket is the set of. Now with set builder notation, the idea is that I'm going to introduce sort of a placeholder, a dummy variable, where then I'm going to describe the pattern that that the pieces of this set have to adhere to in order to be in this. And I'm going to do it in terms of that dummy variable. So this is the set of all X, meaning my X is my dummy variable, so all things, I'm going to call them X for right now. This is where math notation is very dense, so it can be hard to sort of write out all of the description because it sort of blows up a bit. So the two colons or consequent or sort of identically the vertical bar, this is such that. So I'm breaking it down into little pieces right now. And this thing here, I will describe in more detail soon, but I'm going to say this is just the sort of property that we require. Okay. So in essence, when I wrote this set, what I've written is the set of all X such that this is true. So if there's a value, if there's something I could plug in as X where whatever this property is true, it's in this overall set. If it's not true, then it's not in this overall set, okay? And just for the sake of space, I'm going to copy this down here and discuss what that means, because again, these are probably all symbols that you're not familiar with. So obviously, I say all, but the X you're likely familiar with, right? Just our dummy variable. This weird looking almost E, it's sort of like a small C floating with a line in it. So this is an element or member of. So this is saying X is an element of, and again, crazy dense notation here, the Z. So for very, very common sets of things, so the set of all real numbers, for example, things that are very common to run into, they sort of get their own special symbol as a set. And this is exactly that situation. So the Z is the set of all integers. So if you remember, an integer is all your whole numbers with 0 and all the negative whole numbers. right? So negative 1, 2, 3, 4, 5, 6, etc., 0, and 1, 2, 3, 4, 5, 6, etc., okay? So we could read this as x is an element of the set of all integers, although we wouldn't say that mouthful. We would sort of condense that down to x is an integer, okay, as sort of shorthand for that thing, right? If it's an element or member of the integers, the only way you are in there is if you are an integer, so x is an integer, okay? So what that means up here is x is a member of this set, right? The set of x such that this is true, such that x is an integer. So that means that this set is composed of things that are integers, and only those things. But if that's true, right, if this is only the set of integers, right, this is the set of things that are themselves integers, that means that this literally is just the set of integers. So I could say this is a bit redundant because the only property it has to have is that it's in this set, which means I've just redefined that set, okay? So why do we care, right? What would be an example where it wouldn't be some sort of trivial thing like this? So let's see an example of that. How about the set x, right? The set of all dummy variables. And I'm going to throw a small curveball here. I'm going to say all dummy variables which are themselves an integer such that, and I could say x greater than 17. Okay. So again, I'm looking at, right, the set of all x that are an element of the set of integers. So this is here all, so actually let me write out like the full thing here. So the set of so that's the open brace, all x, where x has to be in the integers. So I could say all integers x, meaning I'm looking at all the x which are integers, such that, so that's the colon, right? And then I have to have this property be true, such that x is greater than 17, strictly greater, right? So this is only integers, strictly greater than 17. So it'd be 18, 19, 20, etc. Okay? And if I want more than one piece here, like I want more than one property, so let me maybe show a slightly more complicated one. Let me modify this slightly. Let's say I wanted x greater than 17, and I wanted that let's say square root of x is less than, let's say greater than, let's say less than 10. So if I did this, right, it would still be the set of all integers x such that x is greater than 17, only now I would say and the square root of x is less than 10, right? So if the square root of x is less than 10, then that means that x itself has to be less than 100, right? So this would be x is strictly bigger than 17, but strictly less than 100. Okay? So there are a few other things I want to talk about, just sort of with common things with sets. So there'll probably be a quick editing break here while I erase all this. So abracadabra. I'm probably not where I was before, but that's fine. All right. So we've been talking about sets. We went through the lists and set builder a second ago, probably literally since, editing. So there are two sort of things I want to sort of mention just sort of common things for sets in general, just so that we're all aware. So let's say we have, for example, A is the set 1, 2, 3, and B is the set 1, 4, and 5. Okay. So we can put set stuff together, and we can sort of look at stuff that is common to sets. Now, we can't add sets together or subtract sets together because that is sort of that's stuff that we do with numbers, and we do it differently with sets. So these are sort of analogous in some sense, but it's important to draw the difference between the two sort of types of actions. So the first one we're going to look at is called the union of sets. So union with U is literally, we just write it basically with a little u, but without the tail. So the union of A and B would be written A, little cup-looking thing, B. So this is A union B. And this is literally just everything in A and everything in B. But remember, we don't want to rewrite the same thing twice, right? So I would write everything in A, 1, 2, and 3. And then I'd write everything in B that isn't already listed, right? So 1 is already there, so I'm not going to write it again. 4 and 5 are not, so I'll write those in. Okay? It's worth a note when it comes to list notation here, and really any notation for sets that you're doing, that the particular order doesn't matter. Meaning, like, if I wrote 1, 2, 3, 4, 5, or like 1, 3, 5, 2, 4, or 5, 4, 3, 2, 1, these are all the same set. I don't care what order they're in the set. Okay? The next one is called the intersection. So an intersection, we don't use I because that's really hard to read, so instead we use N, and we're not very clever as math people. So A, little cap or N looking thing, B. So the intersection of sets are where the two sets are the same. So in our example here, I write down all the things in A that also show up in B, right? So I basically go through A and go through B and say, okay, is 1 is in A, is it in B? Yes. 2 is in A, is it in B? No. 3 is in A, is it in B? No. So that's it, right? Because 4 and 5 were not in A, so I don't need those either. So this is just the set of 1, and that's it, okay? There are a bunch of other operations. There's only one more I'm going to actually cover. The other ones aren't going to be used in this class or in calculus, so you may see them if you end up going to, say, a sets and logic class or something in the future, but you won't need it anytime soon. So the last one I'm going to talk about is the set difference. So this one's a little weird for two reasons. One, the notation is a little weird, and two, it's important how we're distinguishing between sets and between numbers, okay? So set difference is sometimes written as, I'm going to put this one in quotes because I won't be using this one, A minus B. Now I don't use this particular notation because it actually generates a lot of confusion because minus, right, this negative thing is something that we tend to actually associate with numbers, and so you might try to do something like the numbers in A minus some numbers in B and do some weirdness, and that's not what we mean here. The other way that we notate it, and the way I mention this because this is a common notation to see. So you can see this in textbooks and in your future calculus classes or something. So you should be aware of it. But in this class, what we're going to be using is the sort of more standard notation, which is A set minus B. So you're going to do set minus B. So note this is, if you use a fraction sign, it usually goes the other way. So this is the sort of opposite direction from a fraction notation. And what this is it is the set of stuff that is in A and not in B. So you go through the things in A, kind of like we did up here, only if you find it in A and in B, you don't list it, right? So you look at it, stuff in A, you say 1, is 1 in B? Yes, okay, we don't write that. 2, is 2 in B? No, okay, then we write 2. 3, is 3 in B? No, okay, then we use 3 as well. Okay. Now there's a bunch of ways to manipulate these things, but sort of in general, that's not really something we're going to be doing much in this class. Mostly what you want to know how to do in this class is how to understand the intersection and union primarily, and every once in a while you might need this set difference idea, okay? The other thing I want to mention, and I'm going to show some examples of this as a result, but some other stuff that you should know. I mentioned a little bit ago in this video that there are symbols that we use for the really common sets that we run into. So we saw one of these. So Z. So this is the set of all integers. So commonly, so this Z, it looks like a Z, and that was actually kind of badly written. In the text, there are sort of nice computerized versions of these symbols. But if you notice, I write it by writing a Z with sort of a longer bottom, and then I double bar it at the top there. So that's what this one looks like. And this will be common theme throughout. And to be very explicit, if I were to write this in the sort of list formation, where I'm going to do the ... example, so it would be, let's say, -3, -2, -1, 0, 1, 2, 3. So it's basically sort of your whole numbers going infinitely positive and infinitely negative, okay? Now, sort of a little smaller than this one, although not, because infinity is weird, but that's not something we have to worry about in this class. We have this double bar n looking thing. So again, it looks like a normal n, but with sort of an additional vertical bar on the side here. This is the set of natural numbers. So again, if you're not familiar with the natural numbers, these are just sort of the positive, and I mean strictly positive, integers. So this is the set 1, 2, 3, ... Now again, this is worth a footnote here that some math people like to throw 0 into the natural numbers, some do not. And math people, because we're weird, we get into arguments with each other over this. In this class, and indeed in most classes, 0 is not a member. That being said, it's never a bad idea to ask, future math teachers, like if you have, if you take calculus, you may verify with them if this symbol comes up, do you include 0 in the natural numbers or not? Almost certainly they'll say no, just 1 and up, but again, there are people that do. Okay. Now there's one that's sort of in between these two, which I left out because I like the sort of natural way this looks, but I'm gonna write it down here. So this one is a Q, but with a little diagonal bar on the side here. This is the set of all rational numbers. I'm just gonna write num. So basically, i.e. fractions. Where when I say fraction, I mean it's gonna be sort of an integer divided by an integer, right? A whole number over a whole number. So I'm not going to look at like pi over 2. That's technically a fraction. But when I say fractions in this context, what I mean is, only whole numbers. I'm not going to, pi over 2 doesn't count, okay? And last but not least, look at R, which again is this, if you haven't noticed, this sort of double bar thing shows up a lot. So R is, again, looks like a normal R, but you have this sort of extra bar stopping it. And this is the set of all real numbers. So generally speaking, this is the set of all numbers that you would think of until we get to complex numbers, which we'll mention in this class at some point. So common ways you would use these kinds of things. So let's say you wanted to use sort of a domain you wanted to sort of restrict to non-negative meaning you want 0 and positive whole numbers. Whole numbers, not real numbers. Then I could do that by writing it out, right? So, for example, if I put it over here, so I could do something like the list form, right? 0, 1, 2, 3, ... So this would be one way to write it. This would be the list version. So list. I could also do the set builder. So to do that, I would say, okay, I want all numbers x. And I could do x in z here, or I can make it a condition elsewhere. I'll do x in z here, such that. So I want all integers, but I don't want negative integers. So I want that, let's say, x is strictly, actually let's do greater than or equal to 0, just to make it look nice. Right, so I'm only looking at whole numbers that are 0 or bigger. That would be the same. Instead of writing it like this, I could also write this as just the set of x such that x is an integer and x greater than or equal to 0. So I write this as saying, it's common to see it like this, so you should know how to read these things, but it is equivalent to doing it this way. You don't have to do it that way. Okay? But there's another way I could write this that's sort of a little easier, which is using these sort of unions and intersections. So instead of doing this, this, or this, I could also write it as I want all the natural numbers, n, but that leaves me missing one, so I want n union 0. But I don't want just 0, I need, because union is between sets, I need the set of 0. So I need to make the open brace, which that was terrible. Let me try that again. Oh boy. So brace 0, close brace. Right, so it'd be n union the set of 0, not just n union 0. That's not something that makes sense. Okay? And the very last thing, last but not least, let's say I wanted to look at the set of, so what if I wrote, so let me maybe do this out. Again, I'm gonna section this off. What if I did something like, let's say z set minus r. So what does that mean? That means I'm going to look at integers, but I'm going to remove all of the real numbers. And this is kind of weird, right? Because all integers are real numbers. So I've effectively removed everything, right? I started with some stuff, and then I removed everything from it. What could that be? So it's not the set of 0, because 0 is a number. 0 is an integer, but it's also a real number, and I've removed that. So it's not 0, but it's sort of the nothing, right? We're used to thinking of nothing from a number standpoint as 0. For sets, this idea of nothingness is what we call the empty set. So it's this 0 with a line through it. So if you're familiar with, it's one of the Greek letters, if you're familiar with those. So that is going to be, I'll write it up here as the last sort of symbol. One typically writes it with the diagonal slash, but you can write it with a vertical slash. It sort of depends. It's not theta, just to be clear. So this is, we call this the empty set. So this is the set that contains literally nothing. There's nothing in it at all. Okay? All right. So with that, we've talked about how to build them, how to combine them, how to write them, and common forms of them, of these sets. So that is that.